are good to go. So this is supposed to be class 1, but this is week 8, class 1, chapter 5, introduction to hypothesis testing. All right, so continuing on with our look at hypothesis testing, keeping that end goal in mind, keeping the sort of reason why we're doing all this in mind, and that is to open up psychology for everybody, to be an all-inclusive science that is not just reserved for the select few, but is open up to everybody. And without inferential statistics, it would be reserved for the select few. So inferential statistics, what we're doing here today, is what takes psychology from the 12 people in your sample to the entire population of individuals. And as you've noticed, as we've worked through a couple of preliminary examples in hypothesis testing, we are now drawing on all the skills that you have learned prior to this. So we're drawing on frequency distributions to learn about the normal curve. We're drawing on z-scores to calculate where our sample is. We're drawing on percentages to figure out where our cutoff scores are. We're going to see that today. So all of this practice that we've been putting in, this is where it's going to start to pay off. This is where you get that automatic practice payoff, where we can finally start to do the super cool things, like take a look at actual psychology studies and data from those studies in order to, do all the cool kind of ninja stuff that we've been building towards. Now, to kind of keep going with that psychology ninja metaphor, I found this infographic, and this is kind of the steps that you would have in ninja development, training, and recruitment. And what we're working towards is we're working towards doing all these steps so that you're ready to do them, and you're also ready to do this completely alone. So the end goal of what we're doing in this class is for you to be able to do a hypothesis test and do every single step and make sure that you get all of those and you can do them all on your own. So as it is, we have 5 steps in our hypothesis testing procedure. And step number 4, where you calculate your sample's z-score. So you take your sample mean and you find out where that z-score is on your comparison distribution. That you can do. That you have the complete set of skills that are required to do that. Step number 5, where you compare. Step number 5. There we go. Step number 5, where you compare your sample z-score to the cutoff z-scores and make your decision. That you have all the skills to do. That we have gone over. That you have the complete skill set. Step number 1, where we do a null and a research hypothesis. That you have, but only halfway. So you don't have the full picture for that yet. Step number 2, where we figure out the characteristics of the Step number 2, where we figure out the characteristics of the comparison distribution. That you do not have yet. That was completely given to you in the examples that we've gone through. And then step number 3, where you figure out your cutoff scores. That was also completely given to you up to this point. So what we're going to do today is we're going to finish off developing our skills for step number 1, and we are going to introduce those skills that you need to complete step number 3. So by the end of today, you will know how to do the full version of hypothesis, null hypothesis, and research hypothesis. And by the end of today, you will know the full version of how to do those cutoff scores, how to figure out those lines in the sand. And the only step you'll be missing is step number 2, and that's going to come in chapter 6. But we're on chapter 5 right now, so let's get you 4 steps in so you have the complete skill set for those 4 steps. So to do that, we're going to have to introduce the idea of one-tailed and two-tailed hypothesis tests. And that's going to give you your doorway into the complete research and null hypotheses and into the complete lines in the sand and cutoff scores. So once we kind of introduce that concept, we're going to go through some in-class demos. So we're going to take a look at self-esteem one more time, and why we're doing this one last time is going to make sense once we understand a one-tailed hypothesis. And then we're also going to take a look at a study, very famous study, that had to do with eyewitness memory and car crashes. And then we're going to take a look at another study that has to do with whether timeout penalties work for adults. So does it work to put an adult in a corner? Will their behavior actually change? All right, so back to the hypothesis testing process, because we're going to introduce that idea of one-tailed and two-tailed tests. So we have our 5 steps. Step number 1, restate your question as a null hypothesis and a research hypothesis about a population, always about the population. Step number 2, you got to determine the characteristics of your comparison distribution. This is not your population distribution. This is a distribution of sample means. Because you have a sample mean and you need to compare it to a sample mean, it's unfair to compare it to anything else, like a population of individuals. Step 3, determine your cutoff sample score on the comparison distribution. These are your lines in the sand. Step 4, determine your sample score on the comparison distribution. This is where your sample mean ends up on your comparison distribution. And then you compare step 4 to step 3, and depending upon where your sample score ends up compared to the lines in the sand, you determine whether to reject or accept the null hypothesis. So today we're going to take a look at one-tailed and two-tailed, and the only parts of this that they impact are steps 1 and 3. So everything else is the same. It's just step 1 and step 3 that change depending upon whether you're doing a one-tailed test or a two-tailed test. So what are those one-tailed tests or two-tailed tests? So we're going to contrast the two. And before we begin this, I'll just mention that up until now, we've only been doing two-tailed tests. So a two-tailed test is so called because you draw lines in the sand on one side and the other side of your comparison distribution. And by drawing 2 lines, you make 2 tails. You got 1 tail there, 1 tail there. That's a two-tailed test. On the other hand, sometimes you want to do a one-tailed hypothesis test. And in a one-tailed hypothesis test, you only draw 1 line. You only draw 1 line, which means that you only have 1 tail. So sometimes you do two-tailed, sometimes you do one-tailed. Why would you choose one over the other? Well, a two-tailed hypothesis is known as a non-directional hypothesis. And this is used when you're asking questions such as, does your treatment have an effect? So does this treatment change something? Does it go up? Does it go down? Right? So one example for this is social media on self-esteem. People are doing a lot of research on social media and its effects on self-esteem. And there are good arguments that social media is going to decrease your self-esteem because of the constant comparison. There's also good arguments that social media can increase your self-esteem because of your connection to a community, because you can find people that accept you. So what's the effect of social media? Well, it could be 2 directions, right? It might go up, it might increase your self-esteem, or it might go down, it might decrease your self-esteem. So if you're doing studies on social media and self-esteem, you would want to do a two-tailed test because you would want to see, does it have an effect? Maybe it goes down, maybe it goes up. We're just seeing if it does anything. On the other hand, a one-tailed hypothesis test, this is known as a directional hypothesis. This is where you want to know if your treatment has an effect in a specific direction. So, for example, if we made a treatment that was designed to increase self-esteem, we're not interested in the decrease side, right? We're not interested in this tail over here. So if we have this tail, that means that we're throwing away half of our power in our hypothesis test. We're doing an ineffective test. We're missing the truth when the truth is out there. So what we do is we only put our tail into the side that we're interested in. So does our treatment cause an increase in self-esteem? Does this treatment make people better? Does this treatment increase the height of children, right? Will this diet increase the height of children? Will this educational program increase scores? Specifically, we're looking for an increase in self-esteem. Does watching violent TV increase acts of aggression, right? We're looking for an increase in this sense. That's when you would do a one-tailed hypothesis test. So sometimes you're looking specifically for an increase. Other times, you're looking for a decrease, in which case you do a one-tail test as well. You just put your tail on the other side. So does my treatment decrease scores of perception? Does this intervention decrease alcoholism? Does this new way of conceptualizing food decrease intake of unhealthy foods, right? Does the treatment cause a decrease? If you're only interested in one direction, then you do a one-tailed test. So as I mentioned, two-tailed has two tails because a two-tailed test has two tails because you draw two lines in the sand. Two lines in the sand that make two tails. So you have the body, that's the big part, and then you have two tails. In a one-tailed test, you draw one line in the sand. So you still have the body, that's the big part, but you only have the one tail. All right, so at this point, is there any question about the kind of conceptual difference between two tails and one tail? All right. So now we need to know, how do we get these lines in the sand? How do we draw these, how do we figure out these particular lines in the sand? And the way that we do it, what it's all tied to, is your almighty alpha level. And your alpha level determines the size of your tails. And it is so important that it was literally just given the alpha, right? So think about, the alpha dog. Think about the alpha in a group, right? It's the most important one. It was given alpha. That should be a clue that this is an important number here. And this number here determines the percentage of your distribution that is in the tails. So this number here is 5%. So if you have an alpha of 5%, you need to put 5% in the tails. And this is where the work that we did in chapter 4 pays off, because the way that we find the score that's going to put 5% in the tails is we need to go to that unit normal distribution table. So we go to the unit normal distribution table, we find the percentage that we're looking for, so that 5% is in the tails, and that's how we discover what it is that, where those tails are. That's where we discover what those numbers are. So let's start off with a two-tailed test. So I believe it was for a two-tailed test. Let me just take a quick, there we go. All right, let's start off with a one-tailed test instead of a two-tailed. We're going to start off with a one-tailed test. It's a little bit easier to do this first. Okay, so the percentage in the tail equals your alpha. Alpha is in the tail is alpha. They're one and the same. So if your alpha is 0.05, that means that you need to put 5% into this tail. That means that we need to find the z-score that puts 5% in the tail. So we go back to the skills we developed in chapter 4, and we say, all right, percentage in the tail, I've drawn my distribution, I've drawn my line, what is this z-score? This is 5%. So we go to our table here, and we realize that we're in this column, percentage in the tail. We find the number that's closest to 5%, and I'll be honest with you, there are two numbers that are equally close in this regard. There's 5.05 and there's 4.95. For your homework, try both. I think it's this one, but you should try it. If one doesn't work, just try the other one. For the exam, either will work. All right, so just so you know that going in. So what we do is we put 5% in the tail. When we put 5% in the tail, that's the z-score associated with 5% in the tail. So when you do your cutoff score, that cutoff score right there is minus 1.64. Because a z-score of 1.64 puts 5% in the tail, so that cutoff score right there has to be minus 1.64 because it's on the negative side. So that cutoff score would be minus 1.64. If, on the other hand, we're doing two tails is a little bit different. Because, just slightly though, because now we need 5% total in both tails. And what that means is that we got to put 2.5% in one tail and 2.5% in the other tail. So we take the 5% and we split it up into our two tails. So remember, the tails are always as big as alpha. Doesn't matter how many there are. If you have to split up your alpha, you split it up. So we put 2.5 here, we put 2.5 here. We go to our table, we look up 2.5. It's right there, nicely, actually 2.5 this time. So we look up 2.5% in the tail. We go over to the z-score associated with that. That is 1.96. So this is positive 1.96. This is negative 1.96. And you'll recognize that number from our previous hypothesis test, right? The previous ones we were doing had an alpha of 0.05. They were two-tailed. And that's why it was plus or minus 1.96 for our cutoff scores. So that's how you find your cutoff scores. That's how you do step 3, where we're looking for those lines in the sand. So the other alpha that is common, and you should be aware of, because it does have a little bit of a tendency to trip students up, is 0.01. So an alpha level of 0.01 is oftentimes used in like medical studies. So if you're doing psychology on like a pharmacological treatment, you'll choose 0.01 over 0.05, just because we have to be a little bit safer. The key thing to know here is that this equals 1%. All right, make sure that you're thinking of this as 1%, not 0.01, because it's easy to make mistakes with this. It's a lot harder to make it with this. So we're looking for 1%. If it's 1% in one tail, once again, we go to our unit normal distribution table. Once again, we take a look at percent in the tail, and we find the number closest to 1%. This time there's a clear winner. 0.99 is only 0.01 away from 1%. And importantly, notice that this is in percents. All right, it's not in the decimal format, it's in the percent format. So take your alpha and change it to the percent format so you know what you're looking for. So we're looking for 1%. That's the closest we can get. Z-score associated with that is 2.33. So in our hypothesis testing, if we had a decrease that we were looking for, this line in the sand is negative 2.33. If we were looking for an increase, we would draw a line in the sand at positive 2.33 to put 1% in the tail. If, on the other hand, we're doing a two-tail test, then we have to be very, very careful, because 1% divided by 2 is 0.5%. It's 0.5% in each tail. So we put 0.5% in one tail, we put 0.5% in another tail, and that's the number we have to find in our table. So we go to our table. Once again, we scan percentage in the tail. Once again, we get a kind of nasty situation where they're both one away. But importantly, we find 0.5% in the tail. Read the associated z-score, and your lines in the sand will be plus or minus 2.57. Plus or minus 2.57 puts 0.5% here, 0.5% here. So the total percentage is 1% in the tails. Once again, for your homework, give 2.57 a try. If it doesn't work, give 2.58 a try on your, because it's equally far away. On the exam, either one will work. All right, I'll accept either or. Yep.
So for two-tailed tests, you have to split alpha in half?
Yep. Okay. Yep. Two-tailed test, you split the alpha in half because the total amount of tails has to equal alpha. All right, so that was step 3. That's how you find your cutoff scores at which you're going to be rejected. You take your alpha, you put it into the tails. If it's one tail, you put it all into the one tail. If it's two tail, you split up your alpha between the two tails. And then you consult the table, find the percentage in the tail, and then find the z-score that's associated with it. And that z-score is your cutoff score. All right, the other one that changes now is your null and research hypothesis. So your null and research hypothesis before we were doing the two-tailed version, right? So is there a difference between the treated population and the known population? That was what we were working on so far. That's the two-tailed version, right? Does the treatment have an effect? Is there a difference? There's no direction there. It's either or, plus or minus, up or down. So what we need to do now is we need to take a look at two-tailed hypothesis tests and one-tailed hypothesis tests. And the principle for this is that your research and your hypothesis tests have to cover every single possibility that can occur. So when you're taking a look at hypothesis testing, when you're taking a look at possibilities, possible outcomes, right? When you have a, let me just make sure I got this in the right direction. What did I put for, okay, treated. You have a treated population, treated population, treated population. And it has some relation to an untreated population, right? So there are three possibilities for how these things can be related. One possibility is that your treated population is greater than your untreated population, right? Your treatment caused an increase. It has an effect. It made things bigger. Another possibility is that your treated population is less than your untreated population. Your treatment caused a decrease. Your treatment made things smaller. So one possibility is that your treatment made things bigger. One possibility is that your treatment made things smaller. The last probability is that your treatment did nothing, and your treated population equals your untreated population. Those are the only three things that can happen, right? That's it. That is the realm of possibilities. So what we need to do is we need hypotheses that cover each of those possibilities. So we need hypotheses here that will cover all three possibilities. And we only have two hypotheses to cover all three possibilities. So what have we done so far? In the two-tailed version of this, we had a research hypothesis and we had a null hypothesis. The research hypothesis is that the treatment does have an effect. That was the research hypothesis. And we wrote it, and the null hypothesis was that the treatment had no effect. The research hypothesis was written as your treated population does not equal your untreated population. And that covers this situation here. So when we're doing two-tailed, when we're doing a two-tailed hypothesis, your research hypothesis covers the possibility that your treatment causes an increase, because that will make the populations not equal each other. And it covers the possibility that your treatment causes a decrease, because that would cause your populations not to equal each other. So that one hypothesis covers these two possibilities. Your null hypothesis that the treatment has no effect covers the last one. And with those two hypotheses in a two-tailed test, regardless of what your data turns out to be, regardless of what happens, one of your hypotheses will cover that situation. You have yourself a complete test. So that was two-tailed. We've already seen those. This is the ones that we've been working with so far. So you have seen how to do a two-tailed test. You now know that's what we're doing. So the last thing we need, the last little piece, is we need to know what to do for a one-tailed test. Now, as it turns out, there are two versions of a one-tailed test. So this was for a two-tailed. So now we're going to do one-tailed, and we're going to do increase. Sure, and we're going to do one-tailed, and we're going to have decrease. All right, so we have one-tailed increase, one-tailed decrease. So in a one-tailed hypothesis, our research hypothesis is that your treatment makes a change in the direction you want. In this case, it makes an increase. So your research hypothesis is that it makes an increase. Your null hypothesis, and I'll just give you a warning here, your book, I can't exactly remember how it does this. It might stick to the equals one, so just be aware of that for your homework. That's not entirely correct. The research hypothesis is that your treatment causes an increase. Your null hypothesis has to be everything else. It has to be the complete opposite of your research hypothesis. Your null hypothesis has to be that your treatment does not cause an increase. So does not cause an increase is the complete opposite to causes an increase, right? It's everything else that could possibly happen. So if we're asking, oh, does this treatment cause an increase in self-esteem? Does this treatment cause an increase in self-helping behaviors? Does this treatment cause an increase in, violent, aggressive behaviors? Does this treatment cause an increase means that your treated population is greater than your untreated population. Treatment made an increase, treatment made it bigger. So that is your research hypothesis for a one-tailed test. That is covering, your research hypothesis covers that increase possibility. Because of that, your null hypothesis has to cover everything else. So the null hypothesis, the treatment does not cause an increase, is the complete opposite of this, and that is the less than or equal. Because it has to cover the less than. What if your treatment causes a decrease? That's not what we're looking for. That's the null hypothesis. What if your treatment is equal to the other one? That's not what we're looking for. That's your null hypothesis. So your null hypothesis has to cover the other two options. Your hypotheses always have to cover all three options. So your null hypothesis has to be less than or equal to. Again, in your homework, if I remember correctly, they do that incorrectly as equal to. Just be aware of that. Just have that on your radar. In the exam, it's going to be less than or equal to. That's going to be the only options that you have for that one-tailed test. So that's a one-tailed test for an increase. One-tailed test can go two ways. So we have to see what we have to do for a decrease. And in that case, it's the same principle. So we take our research hypothesis, and in a one-tailed test, it's always easier to start with the research hypothesis. So the research hypothesis is that the treatment causes a decrease. That's what we're looking for now, causes a decrease. Does it decrease depression? Does it decrease alcoholic consumption? Does it decrease feelings of anxiety? So we're looking for the treatment causes a decrease. Null hypothesis, complete opposite. Treatment does everything else. Treatment does not cause an increase. A decrease. So the treatment causes a decrease is this one right here. The mean of your treated population is less than. Your treatment made it smaller. That's the research hypothesis for the one-tailed decrease test. Your null hypothesis has to be everything else. So it has to be this situation, and it has to be this situation. It's got to cover every other contingency. So this is greater than and equal to, hence your null hypothesis is that your treatment population is greater than or equal to your untreated population. And that is step number one. So you now have the complete set of skills to do step number three, looking up the table, finding your percentages in the tail, and then finding your z-score associated with that. And you also now have the complete set of every possible hypothesis test, whether it's a two-tailed hypothesis, whether it's a one-tailed hypothesis that's looking for an increase, or whether it's a one-tailed hypothesis that's looking for a decrease. We now have the entire set. All right, any questions on that before we run through some examples? Okay. So let's revisit our school example, because hopefully, if you can recall what we did, you may have noticed that we did a kind of silly thing. We kind of used the wrong test. So if a school calls you up and says, you know what, we are worried about the self-esteem of our children, right? They're not calling you up because the self-esteem of their children is too high. Right? They're not calling you up to see if you have a program that will crush the dreams and self-esteem of these particular students. They probably want you to increase the self-esteem of these students. So if they call you in and you say, you know what, I'm taking a look at your physical education program, and I think I have a treatment that can replace your physical education program with a games program, and that will increase the self-esteem, not change it. We're in no way interested in decreasing the self-esteem of these students. We're only interested in the increase. So in that case, let's revisit our scenario here. So a researcher is evaluating the effectiveness of a new physical education program, games program, for elementary school children. The program is designed to reduce competition and increase individual self-esteem. A sample of 16 children is selected and the children are placed in the new program. After 3 months, each child is given a standardized self-esteem test. For the general population of elementary school children, the scores on the self-esteem test form a normal distribution with a mean of 40 and sigma of 8. So a mean of 40 and a standard deviation of 8. If the sample mean is 43.5, is this enough to demonstrate a significant effect? Assume a two-tailed test with an alpha of 0.05. So that's what we did first. We chose to do a two-tailed test with an alpha of 0.05, asking, does the self-esteem intervention, does this games program make a difference in self-esteem? But notice that we're not interested in makes a difference. We're interested in an increase. So what we did is we did the wrong test. We were only interested in an increase in self-esteem, and yet we did a two-tailed test where we were looking for a difference in self-esteem. And what we essentially did in this test is we took half of our power, we took half of the effectiveness of our test, and we threw it away because we were in no way interested in this result over here. There's no way that we would have ended up with a mean, a sample in this tail over here, and then got excited and started calling up schools across the country saying, hey, do you want to crush the self-esteem of your students? Well, we got a program for you, right? We're only interested in this side. So we don't want to throw away half our power. We want this test. We want the test where we're looking for an increase so that we have the greatest power, the strongest, if you would, magnifying glass to find the truth that is actually out there. So that's what we're going to do this time. Instead of doing a two-tailed test, because we're only interested in increase, we're going to do a one-tailed test. We're going to keep the alpha where it is, alpha 0.05, and we're going to do a one-tailed test. And just to kind of hammer home the importance of choosing your tests correctly, recall that when we did the test with this mean, the mean of 43.5, when we first did this test with a mean of 43.5 and a two-tailed hypothesis, we found no effect. We concluded that the games program had no effect. So remember that. Two-tailed test, we found that the games program had no effect. What's going to happen now that we've chosen the right test, that we've increased the power of our magnifying glass, that we've increased the effectiveness of our test? Well, let's take a look. So for this test, we don't, this is not, I believe, on your Excel quite yet, but just kind of follow along on this one. You'll see it one more time. It's a little bit familiar, but now we're seeing it done correctly, the one-tailed test version. Very nicely, regardless of one-tailed or two-tailed, same 5 steps. Same 5 steps over and over and over again. So that's really nice. Once you got those 5 steps down, everything else is just little tweaks and adjustments. All right, so we want to restate the question. As a research hypothesis and a null hypothesis about the population, we want to know, is there an increase in self-esteem for the game students compared to the general USA student? Not a change, an increase. So we got a direction. So we need a directional hypothesis. We need a one-tailed hypothesis. So the research hypothesis, always the easiest to do in a one-tail. Make sure you do the research hypothesis first. So the research hypothesis is that the games increase self-esteem, right? We're dealing with the increase version of this. Research hypothesis is that the games increase self-esteem compared to the general USA population. So we have our research hypothesis. Null hypothesis has to be everything else. Null hypothesis has to be the opposite. So your null hypothesis then becomes that instead of the games increase self-esteem, is that the games do not increase self-esteem. And notice, this is not decrease self-esteem. This is do not increase, because it covers decrease and it also covers no change in effectiveness. So the games do not increase self-esteem means that the self-esteem for the games population is less than or equal to the self-esteem for the general USA population. All right, so that's the one-tailed hypothesis test. That changes when you're doing one-tailed or two-tailed, so be aware of that. Step 2, determining the characteristics of your comparison distribution. We're going to see how to do that in chapter 6, but that does not change. One tail, two tail, that stays the same. So for right now, it's got to be given to you, and the comparison distribution has a mean of 40 and a standard deviation of 2. The population has a mean of 40 and a standard deviation of 8. They are two different distributions. That is a distribution of sample means. We have a sample mean. We compare it to a distribution of sample means. Keep that in mind because it's going to be important in the near future. All right, so that is our comparison distribution. So now we go on to step 3, and we're going to set a cutoff sample score or critical value. This used to have to be given to you, but now we know how to do this. So now we got to draw the lines in our sand that we will compare our test values to. So let's draw some of this out. So we have our comparison distribution that we just was given to us in step 2. All right, this is where we're going to compare our sample to. And it has a mean of 40, and it has a standard deviation of 2. And it's got a marker that's just done. So it's got a mean of 40 and a standard deviation of 2. Importantly, however, this is not in your textbook. This is not in a table. You don't have this anywhere. So we are going to have to convert that into our z-scores, so we can look it up on a z-score table, so that it has a mean of 0 and a standard deviation of 1. So this is the comparison distribution, but we transform it into this z-score distribution so that we can figure out where our, first off, lines in the sand are. So where are these lines in the sand? Well, we're going to set this cutoff sample score, that line that we're going to compare our study to, and we're going to recall what our alpha was. And our alpha was given to us in the question. Make sure you make a note of what alpha is. And in this case, it was 5%. We want 5%, and we want it all in one tail. So what we're going to do is we're only looking for increases in self-esteem, and we are putting our entire alpha, all 5%, goes into the increased tail. So now we got to figure out what's this number right here. What's our cutoff score? So we go to our table, and we find as close to 5% in the tail as we can do. That's that right there. We find the z-score that's associated with it. That's that right there. So this line in the sand is at positive 1.64. Positive because we want the increase side. If we were looking for a decrease, it would be negative 1.64. That's important. Right now we're looking for an increase. All right, so we have step 3, the target against which we're going to compare the results of our study. That's our line in the sand, 1.64. Step 4 doesn't change from one tail to two tails. So we've seen how to do this before. We need to figure out our sample mean of 43.5, right? So our sample mean of 43.5 is right about there, 43.5. But where is it on our unit normal distribution table? Well, to figure that out, we got to take 43.5 and we have to change it into a z-score. So we got a mean of 43.5 for our sample. We have a mean of 40 for the comparison distribution, standard deviation of 2 for the comparison distribution. We have our formula for a z-score, and we convert our sample mean into a z-score, plug it all in, and we get a sample mean of 1.75. So this score of 43.5, this mean of 43.5, changes into a z-score of 1.75. And the last thing we need to do is we need to find out where is 1.75 here on our z distribution. That's 0 right there. That's our line in the sand at 1.64. 1.75 is somewhere in there. Importantly though, it's crossed the line. 1.75, a z-score of 1.75 has put our sample beyond the line in the sand. It has crossed over into the tail. So now all that's left, once we figured out that it crossed over into the tail, is which hypothesis do we choose? And for that, we go to step 5. And until this is rock solid, keep this slide handy, because you do not want to do all the heavy lifting in steps 1 through 4 and then drop it in step 5 and choose the wrong direction. So if the sample z-score is beyond the cutoff z-score, it went beyond, it crossed that line in the sand, it's gone into the tail. So what do? We accept the research hypothesis and we reject the null hypothesis. So that's our decision. We accept the research hypothesis, we reject the null hypothesis. If the other situation occurred, where our sample mean was somewhere in here, it was somewhere in the body, well then we would do the opposite. We would accept the null hypothesis and we would reject the research hypothesis. As it is, our decision is made. We're going to accept the research hypothesis and reject the null hypothesis. And our final conclusion is that our games program does increase self-esteem. Our games program does make self-esteem higher. It does increase the self-esteem of our students. All right, so any questions on that run through of a hypothesis test? All right. So what I want to do now is I'm going to turn it over to some in-class practice time. We got like 25 minutes left. This is a good chunk of practice. So what we're going to do for this is there are two questions that we have for this kind of practice session. One of them has to do with eyewitness accounts of car crashes. This was a very influential study done by Lach and Palmer that basically changed the way that psychologists think about memory. So there's the setup for this. So you have all the information that you need. You have your you have your sample means. You have your one-tailed test with an alpha 0.05. You have your population distribution. Importantly, you have your comparison distribution. So what I'd like to do for this remainder of today, go through each of these two examples. The first one is Lach and Palmer. The second one is the timeout study to see if timeout is effective for adults. Depending upon where you are, I would suggest kind of challenge yourself to go to the next level. So if you're still kind of, really struggling with the steps, do a follow through. Like all the steps are there. If you, in the slides, if you want to take a look. If you're feeling a little bolder, just kind of have the 5-step procedure there and try to do it on your own, to begin with. Just knowing that it's there for a fallback. And if you're really struggling, feel free to call me over and just sort of, if you're kind of stuck, if nothing is really making sense. But just so you know, this is what a large portion of your exam is exactly going to look like. All right, so you will get a description of your experiment. So in 1974, Loftus and Palmer conducted a classic study demonstrating how the language used to ask a question can influence eyewitness memory. In the study, 15 college students, blah, 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 blah. It will go through that. It will tell you, this is something to be very clear about, it'll tell you which test to do. So in your homework, you're going to probably see situations where they're like, oh, which test should you do? And it's up to you to make a choice. In the exam, I will tell you, do a one-tailed, do a two-tailed. I just want to know, can you do a one-tailed or a two-tailed? And you will be given the alpha. Then what you're going to need to do is you're going to need to fill in the rest of the information. So, null hypothesis and research hypothesis. Delete the symbols so that the symbols remaining are the ones that you want to cover all three situations. Step 2 is given to you. Comparison distribution is given. I can't use the laser pointer because Excel freaks out. Comparison distribution is given right there. The only difference between this and the exam, this is your kind of like demo into it, your practice session into it. The only difference between this and the exam is that the comparison distribution will be in the description. In the description, you will read the population distribution has a mean of this and a standard deviation of this. The comparison distribution has a mean of this and a standard deviation of that. So be on the lookout for the comparison distribution. That is step 2. Step 3, find your lines in the sand. Go to the table. Find out where those lines are. Step 4, find your sample z-score. Calculate out, where's my sample? Calculate out your sample z-score. And then step 5, depending upon your sample z-score and your cutoff score, choose which one is the correct answer. So that's the Loftus and Palmer study. This one is the same idea with timeout for adults. So let's turn it over to practice time. Give those two a go. You will see the correct answers. We don't have it updating here. Oh no, we do have it updating here. Look at that. I mean, better than I thought. We have the answers updating here, so you can scroll on down. There we go. You can scroll on down. And importantly, you'll notice that there is this points here for different conclusion. To get full points on these questions, your conclusions have to be different. If you accept both the null and the research hypothesis, sure, one of them is right, but that does not indicate that you know how to do a research and a null hypothesis conclusion, so they have to be different for full points. All right, so practice time is officially on. As I said, call me over if you need any assistance, and let's see if we can do these in a kind of more independent situation. All right, so just real quick as we're winding down today's class, just a couple of reminders. So you are now ready to do homework assignment number 8. That's the chapter 5 homework. So you got all the skills that you need to. You got the complete set that you need to do that one tail, two tail. You'll see that in that homework assignment. So that's going to be due March 4th by midnight as per usual. Chapter 5 post-test. Once you complete your chapter 5 homework, you'll be ready for that. That's due March 9th. So that is due right before midnight before the exam. And as well, if you are taking advantage of the MyStat Lab study plan, if you're getting those mastery points to supplement your pre-test points, just be aware that the due date for that is midnight before the exam. So if you're doing it for chapter 4, the due date to do those study plan points is midnight before the exam. If you're doing it for chapter 5, once again, midnight before the exam. Other than that, that's what I wanted to cover for today. So if there's any final questions, let me know. But that is it.